So this is part 2, and you'll notice there'll be a substantial speed difference between the first one and this one. The first one, some of you might be thinking to yourself, I didn't get anything out of that, you went way too fast, and I'm not going to be taking the MCAT. So that's the point of the second video, is now what I'm going to do is actually go through step by step and show you what is going on, and then this way you can kind of tease out all the principles and the reaction mechanisms that might be beneficial if you're just taking the class and not the MCAT. So let's go ahead and bring this back up. And here we go. So, as we've talked about in the first video, we're going to start out with this dicarbonyl compound, such as this. Now the first thing is we're dealing with this base, this sodium methoxide. So really what's important is not the sodium, we'll put it in there, but you can really think about this as a methoxide is this minus charge, and the sodium is just a counter ion. And we'll highlight these as lighter gray. We have to remember that each carbon has 4 bonds. So we have 2 hydrogens there that are just kind of understood when we draw the line. And this methoxide could come in and deprotonate one of these. We can push that negative charge up there. And that'll give us an intermediate species, which looks like this with the minus charge. And if we wanted to, I guess we could go ahead and draw a resonance structure, so we'll use that in green. So this minus could go here. We can push that up there. And let's see, what color should we use here? We'll use gray. Why not? So one of the intermediate structures could look like this. Minus. And if we did this properly, we would say sodium plus. So the reason I'm just showing you this is that once we deprotonate, that this negative charge can go up on this side, or we won't write it. We can imagine the negative charge should go on this side, and we would have the double bond here, and we would have the minus charge here. But continuing with the mechanism, so what we have now is we're going to add this dialkyl bromide. So let's stick bromine, and this can come in and do an SN2, which will come in here, kick out that bromine, and that will give us this intermediate structure, which is our 2 carbons with our bromine left over. And if we just keep track of things, I'm trying to figure out the best place to put this, what we're also going to get is plus sodium bromide, because we used the sodium from here and the bromide that got kicked out. Now this reaction, they don't tell you, but there's going to be an excess of sodium methoxide in there. Jeez, I keep seeing ethoxide. So we can imagine, just like we did before, we've got our sodium plus, O minus. We have another understood hydrogen here. So I'll write that on there. This can come in here, grab that hydrogen, pushing that negative charge down on there. We'll try to be as thorough as possible. So we'll have our O minus, we'll have our alkyl bromide, and we're going to definitely generate our anion there. Now this anion is going to do, there's 2 reactions that we can think of that happen in organic chemistry. There's intermolecular, which means between 2 different molecules. So this is an intermolecular reaction where we have 1 molecule and 2 molecules. This is considered an intramolecular. An intramolecular means that it reacts within itself. So this negative charge that's on that carbon can now just come around here. This is obviously an SN2, so we're going to attack that carbon, kick out our bromine, and the structure we will get looks like this. So if we just kind of track carbons here, we can imagine we've got 1, 2, 3. We've got our 1, 2, 3. Alright, so now we're at this stage right here, and I'm just going to recap from the last video that the reason this is 1/2 a molar equivalent is because what they're doing is they're setting up either, in this case it would be a 1 to 0.5, but really what they're trying to show you is that it's a 2-to-1 ratio, so you're only going to get 1 starting material, 1 dicarbonyl compound, to one alkyl bromide. So then that way you can get this intramolecular cyclization to form this three-membered ring. Now to finish this off, so we're at this stage, now we're going to treat this with acid and water. And what happens here is, we can say first is, how do I want to do this? So we're going to have an acid source, and the lone pairs on here can grab that. And this is just one of these, so we can get here H plus. We still have our three-membered ring. And now we have water. And this water can come in, attack this. We can kick that back up. And that's going to give us now OH. Still have our three-membered ring. This. And we have water down here. And let's see here. What might be the best thing to do? Let's go ahead and what if we grab this, copy this, delete, and we'll move this. Okay, this will give us some more room here. Alright, so we were at the stage where we protonated. Let's get this. We protonated this carbonyl. Now water is going to attack, and now that we've pushed these electrons up here, this water is going to be positively charged. And now at this stage, what can happen is, let's see, where's the best way to go here? So I guess one thing I can point out is anytime you do an acid-catalyzed reaction, when you use an acid source in the mechanism, you have to regenerate that proton. So in this case, what we can imagine here is we've added our water, and at this stage we can lose the proton to regenerate acid catalyst. And in this, we'll just write this as an aside down here. When you typically see H plus and H2O, what they're really saying is that this is H3O plus, is another way you can look at it. So what we've done here is we've added our acid, and we still have, oh, this is our acid. We've added our water. Now at this point in time we want to regenerate our acid catalyst. Something typically will come in and grab that. Typically water will come in and grab this hydrogen. But what I'm going to do just for this sake is I'm going to say we're going to take our hydrogen and we're going to lose that hydrogen. These bonds can swing down here, and then at this stage we can kick out this methoxy, giving us, to draw it the way I've got it here, OH and O-methoxy. And we can imagine that the exact same thing happens again. So just for simplicity's sake, we get this. Now at this stage we need to rearrange this. So I'm going to draw a couple arrows. We need to rearrange the structure so we can make it look a little different. So we're going to actually put our OH up here, our carbonyl down here, our carbonyl here, our OH, and then this. The reason I'm doing this is because it's easier to see why this decarboxylates. So the lone pair on this oxygen, this carbonyl, can now interact with that hydrogen. And what this does is under heated conditions, so we'll just put delta, this decarboxylates, and you can see here that we've got a, we can mark these, we have a 1, 2, 3, 4, 5, 6. Anytime you can set up a, we could consider this a 6-membered transition state, particularly in this case, they're very stable, and it sets up a perfect system to actually decarboxylate. So what happens here is this oxygen grabs that hydrogen, this swings down here. Now we formed another bond to this carbon, so we can, if we have 2, now we've got a total of 4, so something has to give, and rather than pushing these electrons up here, this now swings down here, forms a double bond, and then now we can actually form a formal bond with that oxygen hydrogen right there now that that swings up. What's that structure going to look like? So we're going to have a triangle, Remember, we formed a double bond here, so what this is going to look like intermediately is this OH. We have OH here, but this can obviously tautomerize to give us OH, such like this. So really what's happening here is this hydrogen is just getting transferred to that center right there. And you can see here that now that we have the structure. So as I was going through this mechanism, there's one thing that I would like to point out back up here. So let's delete this. Let's bring this back. Let's move this up here. So what I had said was, colors here, is that when we lost at this stage, when I just said, okay, let's just assume that our hydrogen just leaves. What more than likely happens, to give you a better mechanism, something that's more complete, now that I look at what I was doing, because as I'm making this video, I'm just off the cuff, I haven't practiced this, so this will kind of give you an idea of how tutoring sessions go. I typically don't ask the students to send me the information ahead of time because I like to kind of work with them as they go through. But anyway, that's an aside. So what more than likely probably happens here is there's probably an internal transfer where, just to make this, to set this up, so let me go ahead and put our positive charge. We have a positive charge here. It's more than likely an internal transfer of this hydrogen, so this hydrogen can transfer onto this methyl group here. And what that'll give us is now H. That's still an H. We have our cyclic system, and we have our methoxy. And now this is positively charged. The reason that I do this is because now what we're doing is we're setting the stage, and we still have our OH down here, is we're seeing now that when we protonate this, this is a much better leaving group. So methoxy by itself is not a good leaving group because we would have a negative charge on that. But if we can protonate that in any way, now we have a positive charge. And anytime you have a positively charged part of the molecule that initially was a carbonyl, that's going to set up the stage for a really, really good leaving group. So at this stage, it doesn't matter if we, for example, regenerate our acid catalyzed from this OH or this OH. It doesn't matter. But just also, once again, for complete clarity and to be complete with the mechanism, we're going to have water floating around here. This water now can come in here, grab this hydrogen, this can collapse, and rather than kicking out our OH, we're going to kick out that, and that's going to give us, let's see if we can draw everything here, we're going to have this, there's our OH, there is our cyclic system, there is our methoxy, and now if we just add everything up, we're also going to have plus, that's our methanol, and we can see here that we also have our H3O+. So we can see from this that we've regenerated our acid catalyst, we've lost our group, and then we've got this, and then this can be followed up since we've already done it. We'll just go through, we'll do this in blue, but we're going to make sure that we do our hydrolysis on both sides, and then we set up that perfect system with the 6-membered ring to give us our final product.